Please be seated. I open the meeting of the doctoral committee of Sajid Mohamed. Could you please come forward in front of the audience? Eindhoven University of Technology is always very thankful for the committees, for the PhD defenses to read and study the documents that the candidate provides, especially also for our committee members from abroad, from other universities. So I very much would like to welcome Professor Chakraborty from UNC Chapel Hill in the US and Professor Jans from the Technical University of Vienna. Thanks a lot for being part of this committee. So in the coming meeting, the candidate will have the opportunity for the opposition of the PhD defense, and we will start right away with the first question. So I would like to ask the first promoter, Professor Basten, to ask the first question.
Dank u, mevrouw de rector. Geachte promovendus, could you maybe in about 10 minutes explain to the audience and the committee what your research in the last 4 years has been about?
Hooggeleerde promotor, bedankt voor je vraag. Highly learned members of the committee, family, friends, and colleagues who are present here and also online. It is my pleasure to welcome you all to my public defense, and I sincerely thank you all for attending. Cameras are and will be prominent in the future. Did you know that the YOL estimates that the camera module market will almost double to 60 billion by 2027, and it will be more prominent in the automotive, medical, and industrial domains. Today, a Samsung Galaxy S22 Ultra phone already has 5 cameras, and a Tesla Autopilot has 8 cameras. Now let us look at the type of a camera-based system called the image-based control system. An example is the lane keeping assist system. It is a camera-based system that tries to keep your car in the lane. Image-based control systems is a class of data-intensive feedback control system whose feedback is given by camera sensors. I call this multiprocessor image-based control simply because it's executed in a multiprocessor platform. The control objective for the lane keeping assist system is to control the steering angle automatically to keep the car within a lane. Now there are 3 prominent tasks here. There is image-based sensing and processing, control, and actuate task. In a timing diagram, these 3 tasks can be mapped to a single processor as shown here. In an image-based control implementation, the camera input arrives periodically with a period fh. The image sensing task takes a long processing time. As you can see here, the S takes a much longer time than C and A. And there is the time between the start of the camera sensing to the next camera frame sensing is called the period. And the time from the start to the end of the actuation is this delay. So now the question is how to improve the system performance of such an image-based control system. One thing you could do is you could reduce the delay and the period. So that comes to the first question that I want to explore in my thesis. So the image processing platforms nowadays mostly use multiprocessors. So one of the questions I want to explore is how to utilize the given platforms efficiently. Let us look at another example of a lane changing system, and this was done by a crazy developer. The image processing task here involves just counting the number of vehicles in the image. And what you do is, based on the number of vehicles, whether if it is high or low, you change the lane. Now I have a task for you. count the number of vehicles in this image. Done. Now count the number of vehicles in this image. Just give it a try. What do you observe? You could count for the first one instantly. But for the second one, even though it's the same application, you need a much longer time. So what we notice is the image processing delay is variable and often long. That comes to the second question. So the image processing delay is application specific. So how can you effectively consider the application characteristics to improve the system performance? So the actual problem I try to address in my thesis is that there is a long and variable delay in processing the image and getting a result. So I formulate my research question as how to cope with this long and variable sensing delay for a given platform allocation. And to solve this, I use a model-driven optimization approach that considers both platform-specific characteristics and application-specific characteristics. So for the first three contributions, so it involves a scenario and platform-aware design flow. So what we call a sequential implementation. I think I missed one slide. I think for me it's I'll just go back once. Okay, so so here this is what is called a sequential implementation. So you execute in just one processor, and then in case you have two processors, one thing you could do is pipelining. So a pipe is a sequential execution on a single processor. And by in pipelining, what you do is you replicate the pipes. So for example, in the sequential implementation, you dropped 3 frames. But by doing a pipeline implementation, you could drop alternate frames instead of dropping the continuous 3 frames. Another one you could do is parallelization. So if you have two processors, you could execute some task in parallel. So for example, here in this image, I could divide the image into 2, and the first processor could count the first part and the second processor the second part. So what you notice here is the period and delay varies based on the approach that we use. And the third approach you could use is pipeline parallelism. That is, we combine both parallelization and pipelining. So for example, one pipe could be like this. So you have a parallel implementation, and then you replicate it as many times as you have the number of cores. So what we achieve here is in this implementation, you would not be dropping any frames. You could also do what you could also do is optimize the scheduling, because you notice that there is a lot of free gaps. So you could also optimize the scheduling. And one of the contribution is using model transformations. So in here, the number of pipes you had is 3, and the number of parallel cores per pipe is 2. And now what do you gain by doing all this? So this is a plot which shows the image-based control system performance as a normalized MSE, so mean square error. So a lower mean square error is better. And on the x-axis, you see the number of available cores. So for a sequential implementation, so you see it on the top on the 1. You only have 1 core, and it needs a normalized since it's 1. And you could already see for when you just do parallel or pipelined execution, we improve a lot on the performance. So it already shows around 30% improvement. And if you have more cores, you could gain even more with pipeline parallelism. So my next contribution is considering application-specific aspects called the image workload variations. So earlier you tried to see that there are 2 different images. So we can say that if the number of cars in the image increases, the image workload increases. In my thesis, I propose a Markovian jump linear system formulation for considering the image workload variations. So for the next contribution, can you still count the number of cars in this image or vehicles in this image? I think you still can. But what we did here was we traded off accuracy for time. And we do it using an approximation-aware design. And you could do this also for the lane keeping assist system. So here you see a sequence of steps for an image signal pre-processing pipeline, but you could also approximate by skipping some of the stages. So in approximation, we mean is we skip some stages so that we really do not need the final image. We could already do our application with an intermediate image. And in my thesis, we already show around 44% improvement in image-based control system performance compared to accurate implementation. So the key takeaway message I have is, in this thesis, we explore how to efficiently use the given platform and application-specific characteristics to maximize the image-based control performance. And this slide highlights the contributions that I have made in the thesis. On the right side, you can see platform-specific aspects. So there is parallelization, pipelining, and pipeline parallelism. And on the left side, you see application-specific aspects, which are workload variations and approximation-aware design. Thank you. I hope that answers my question.
Thank you for this nice summary. Yes, it's clear.
Okay, so thank you very much. Then we will continue with the opposition, and I would like to ask Professor Chakraborty to continue with the questions to the candidate.
Thank you very much, geachte Promovende. I would like to start by congratulating you for this excellent thesis, and I would also like to note that currently there is a lot of importance attached to autonomous systems, and vision-based control plays a very important role. So the work you have done is very timely and very relevant. So in your work, of course, image processing algorithms play a major role. So my first question, or rather a discussion, is what I would like to have, is can you give a very quick overview on what kind of structure image processing algorithms have? And in particular, can you comment on where does parallelism and pipelining and also approximations play a role in modern image processing algorithms and architectures?
Hoogele, the opponent, bedankt for your vraag. First of all, thank you very much for your kind words and the compliments. So if I understood correctly, you want to ask how the image processing algorithms, you can implement parallelism, pipelining, and approximate computing in a general sense, or?
Yes, and also taking into account modern architectures like GPUs, which are increasingly being used for image processing algorithms. So how would parallelism, pipelining, and approximation play a role in modern image processing algorithms and architectures?
Okay, so yeah, I can. So from my experience, what we have noticed is, so the platforms, for example, the high-end platforms nowadays have TPUs, GPUs, and so on. So in image processing algorithms, the structure itself is like it needs you process pixel-wise typically, or so that's like traditional algorithms. So how you compute is you process pixel-wise, and by structure, this can be mapped directly to a GPU or so the existing modern platforms. And also nowadays we also have image processing algorithms which use DNNs or deep learning networks. So the deep learning networks, so for example, one platform is a TPU or an NPU or a tensor processing unit or a neural processing unit. So you could have these algorithms where each node is a tensor or each block is a particular architecture, and you could customize your hardware for these applications. So in essence, I would say that we could, so each of, for the traditional algorithms, you could have some dedicated hardwares for it, and also the same for DNNs or other types of algorithms. So does that answer your question?
Yeah, it does. It does. And so in the kind of applications you are talking about, there is the image processing would sometimes do some sort of a estimation, right? Like how much is the deviation from the lane, or what is the distance between the car and the car in front? or there could also be recognition, like, whether there is a obstacle in the front. So can you briefly discuss what would be the difference in the two classes of algorithms, and in particular, which is the class of algorithms that you are particularly interested in your work?
Okay, that's a good question. So in my work, so let me start with that. So in my work, the kind of algorithm I consider is both. Actually, I consider both a traditional algorithm. So for example, in the lane keeping, what we do is we take an image. So we do, let's say, first a perspective transform, then we do some edge detection, and then we fit a lane. And that's the first kind of algorithms. And I explore how you could use that or optimize the performance of those algorithms when you implement. And the second one, I also consider neural networks. So for example, a lane net which is deployed on an industrial platform. So by class, I would say it's more on detection, like edge detection and tracking. So that's the kind of image. So it's more on image classification in that sense, but more it's like tracking, object detection and tracking. So that's what I'm mostly looking at in this thesis.
So you already mentioned that today there are a lot of neural networks that are being used for image processing, in the context of these applications that you have studied. But this is a fairly new development, right? Traditionally, there were lots of other sorts of image processing algorithms. So in the context of your work, can you discuss in particular how suitable would be the machine learning based image processing algorithms for things like parallelization or pipelining or approximation? So if I have a neural network doing image processing, where does parallelism, pipelining, and approximation happen?
Ja, so hooggeller de opponent bedankt voor je vraag. So in a neural network, so what you do is you have a convolutions. So if you have a architecture that, like for example, an FPGA, then you can do the convolutions in parallel. And the pipelining, you could also pipeline the different layers. So if it is not fully connected, of course, if there is a sparsity, then you could pipeline it. And the approximation is you could approximate the weights, and also you could say that the particular layers may not be needed. So for example, one thing we did as well in the future work is some of the layers you can skip or you can prune the network. So that's also a form of approximation you can do within the network. So within the scope of a neural network, I would say there is immense potential because in the modern neural networks, so for example, recently there was the ChatGPT that has around 175 billion parameters. So that means 175 billion inputs, or let's say, and then you have that much deep networks. So that means like around 175 raised to some 1,000 convolutions you need. And that is like really huge. So you need, if you could parallelize it, then you could gain huge on the end-to-end latency for the execution of these kind of algorithms.
So does the variability in the execution time happen because of these approximations, or does the variability in the execution time happen also because of other reasons?
Hooggeloorde opponent, bedankt voor je vraag. So the variations, I think it's like two things. From my observations, there are two things that happen. So one is the application specific aspects. Like for example, as I showed, if there are more features in the image, then you might have to process all the features. And the second one is the platform load. So if your platform, let's say the GPU or the NPU where you implement it, if it is having more other applications running on it, that could also affect the execution time. But for the neural network, typically what we notice is once you freeze the network, then the inference time doesn't vary so much. It only depends mostly on the execution, the interference from the other applications. So once you freeze, that means the number of nodes are fixed and also the convolutions are fixed. So if you want to do optimizations, you need to do it before choosing the network. So you could use a neural architecture search or any other methods for that. And then after freezing, you can estimate that the inference time would be within some known bounds.
And maybe I ask a last question, and if you could answer that briefly. So in in most of your work, you have dealt with different kinds of data flow models, like the scenario-aware data flow model. So in light of this discussion that we just did in terms of the kind of image processing algorithms and architectures that are used, can you briefly comment on how easy or how difficult it is to model these kinds of algorithms as scenario-aware data flow models?
Ja, so if you hooggeloorde opponent, bedankt voor je vraag. So if you consider the neural networks, one key challenge is scalability. I think so. For example, it's possible to model it, but then if you want to analyze it, then it becomes really slow. So it is not so scalable in the current way. So you might need some more techniques to make it more scalable. But I do. I mean, yeah, theoretically it's possible, I would say, and yeah, because. Yeah, that's my answer. Yeah,
thank you very much.
Thank you.
Okay, thank you for your questions. I would like to ask Professor Jant to continue with the opposition.
Thank you very much. You can hear me clearly?
Yes.
Geachte Promovendis, first of all, I also would like to congratulate you to your great work. I think you have made a number of very timely contributions, and we have unfortunately only time to explore a very small subset during this session. So let me continue along the track that Professor Chakraborty has started with the questions. So you're looking at time variable algorithms in the image processing pipeline. So I think in particular at the end of chapter 5, you give design guidelines depending on the characteristic or the information that is available and the characteristics of these algorithms. You deploy different kinds of algorithms to manage the processing. So now we have learned that there were a number of different image processing algorithms, classic algorithms, deep neural networks, which have very different characteristics also. So first of all, I would like to ask you from the perspective of what is known and how variable the time requirements are. Can you characterize these image processing algorithms based on how variable they are, how much is known about the execution time?
Ja, hooggeloorde opponent, bedankt voor je vraag. So if I understand correctly, you want me to characterize the variability and in the execution times for classical and deep neural network-based algorithms. Is that correct?
Or if you have a finer categorization, that's also okay. I mean, if you have more categories. So what are the categories you would name here in this context?
Yeah, okay. So so definitely I would say there is classical or traditional algorithms which doesn't use neural networks in that sense. So you just have like you do pixel-wise processing of the image to make some inference out of it. So for me, those two are definitely categories. And then for the traditional algorithms, the variability is a bit high because it depends mainly on the features you have in the image. So if you have more features, then you might need to do more processing afterwards. But in the neural network, once you train it, the variability can be a bit less. So the variability depends only on the platform load in that sense. So I would say that the variability in that sense is, you could do it at design time. So maybe one other, let's say, aspect here is that how you take the image. So if you only consider the neural network, then there is no variability. But you might also have input. For example, when you take an image from the camera, you have an image signal preprocessor. And then if you also have to take that time into account, then that's actually so typical ISP or image signal preprocessing pipelines run on DSPs. So there could also be variabilities there. So depending on, how much, what's the frame rate or the configuration that you set.
Mm-hmm. Can I add here? So where do you see the major source of variability? Is it due to the individual algorithm, like a particular DNN or an edge detection algorithm, or is it due to the overall flow? That sometimes, depending on the state and on the content, a different path through this processing pipeline are taken. Where does the variability mainly come from?
Ja, hooggeachte opponent, bedankt voor je vraag. So I think the variability comes from the flow. So if it is just you only look at a particular path, then yeah, maybe I think the execution times can be bounded without a lot of variability. But it comes from like the particular application part that you consider. For example, in my case, it's a lane detection. So then, so the variability is if you have more cars that is, let's say, blocking the lane, then you might need further processing for it. So if you only do like a typical initial edge detection and overfit, you will see some results. So you will get some results. So that's that part is bounded. But then you know that that result is not feasible. So at some point you might have to do a bit more. So so then that's where the variability I would see in those algorithms. Does that answer your question?
So yes, perfectly. Thank you. So in the design guidelines in chapter 5, I think you distinguish 3 different cases. I think it's in section 5.6.3. And these different cases, they're also listed in this table, 5.1. So depending on the knowledge of the system, you take different strategies. So what can you very briefly explore how likely do you see individual cases? So what is the main case and what will be, let's say, will be cases which will never appear in practice? Can you say something like that, or how do you view the probability of occurring these cases?
Ja, hooggeachte opponent, bedankt voor je vraag. So indeed, so I mentioned 3 cases. So the first one is worst case workload information is known, port distribution is known, and then you have frequently occurring workloads and their transition probabilities are known. So I would say in practice, the second one is more probable. So getting a transition probabilities and then modeling it as a discrete time Markov chain. So that needs a lot of conditions and assumptions. But then getting a port distribution, for example, that's, I mean, if you have some simulations, that's more realizable. So for me, in practice, I would say the second case is more feasible. And definitely the first case you can do always. So you only need the timing information. And the third case, you need much more. So that's where, yeah, so I think if you have the information, you can tune your controller and your design better. But if you don't have it, then, yeah, I mean, you don't have it. That's it.
So a short add-on question. So in the second case, where you have paired distributions of workloads, how guaranteed is this information? So I mean, because you basically rely on, or you want to at the end give real-time behavior. What is the chance that your assumptions or the result from the simulations about these distributions are incorrect, and then this leads to wrong performance and behavior of the system?
Hooggeachte opponent, bedankt voor je vraag. I think that's a really valid question and a good question in that sense. So actually, yeah, we cannot guarantee it. So it's like it depends actually on the curve fitting itself. So if you have a better fit, then it's good. But the control design that we do, that is robust enough to accommodate for these variations. So the control design, in this case, we use switched linear control or a linear quadratic regulator. So they are robust to accommodate for some kind of variations. So when we compute the really worst case, or let's say the worst case to workload, we give some tolerance typically, and it depends actually on the curve fit. And if the curve fit is good, then I mean the tolerance of the controller design should be sufficient to tackle it. And that's why I think also for the future work, I mentioned that the analytical worst case execution time computation and also the curve fitting, that's important. So if you have a better analytical model or fit for the execution times, that always helps.
Okay, thank you. Maybe I have a very short last question. So we were talking about different image processing algorithms. DNNs, deep neural networks, have become very prominent recently. Do you expect in the near future that they will completely replace that classic traditional algorithms, or will we have a coexistence for a long time to be?
Hoogeleide opponent, bedankt voor je vraag. At least from my experience, I think replacing the neural networks may not replace completely because already what we notice is the machine learning operations, so MLOps. So if you want to deploy a neural network in production, in a production machine or in an actual car, there are a lot of retraining and data gathering and steps involved. So there should at least be some level of redundancy, and the redundancy will typically come from traditional algorithms. And I think, maybe for some specific cases, for example, like ChatGPT or so any other, so some specific cases that might be, but in overall, in a generic sense, I would say there will be a coexistence rather than completely replacing traditional algorithms.
Okay, thank you very much. That satisfies my questions.
Thank you very much, Professor Jans. Then I would like to ask Professor Goossens to continue with the opposition.
Dank u, mevrouw de rector. Geachte promovendus, I read with interest that you use the CompSoc platform, which made me very happy. But then you said, well, actually, I can also do all of this with other platforms. So have I been wasting my time for the past 20 years? Why?
Hoogeleide opponent, bedankt voor je vraag. That's a really valid question. So I think so what I show in my thesis is if you have a platform like CompSoc, then you can gain a lot during the design phase, and you can implement the predictability and composability of your algorithms in such a platform, and you can gain a lot. But in industry or in typical markets, you don't get a CompSoc-like platform. So there you only have, let's say, NVIDIA or other kind of platforms. So what I also show in the thesis is this approach can also be used for the other platforms. But what I would point out is you can gain much more, or if you use a composable and predictable platform, you gain much more.
So do you gain in quality of control or in cost or in design time? Can you be a bit more specific? And maybe also relating to Professor Jans's question, where is the variability? So where,
Hoogeleide opponent, bedankt voor je vraag. So I think it's mainly on the time to market. So it's like if you have a CompSoc, then you don't have to do a lot of testing at the production side. You don't have to go through all the tests. You have a proof designed by, you have more like a synthesis kind of design. So you have a proof by correct construction. And because of that, you can already know that the test, you don't have to do a wide testing. So I would say that would be the key advantage for such a platform.
Thank you. So can you then tell me in figure 2.4, you have HIL validation. So you have a nicely formal flow. And then at the end, there is at least on the side, but I assume it's at the end, you have an HIL validation. Why is that needed? And what happens if it fails?
Hoogeleide opponent, bedankt voor je vraag. So at least for this particular case, it was needed mainly because I was also using an industrial platform. So for an industrial platform, you really need it to show that, you can take into account these variabilities. So, and the variability comes, as pointed out, based on the image workload and a few other factors there. But if you have a CompSoc platform, the HIL validation you typically need to do for certification purposes or for some kind of, let's say, you need to show the proof of concept in that sense.
Okay, so in an industrial platform, if HID validation fails, to which step would you go back in this flow? Would you to modify your application, or is it enough to change your controller configuration? Where would you suggest there would be some kind of a back arrow?
So the back arrow there goes now back to the controller configurations and mapping configurations. So, and then that's where you will go, because there you already have chosen some set of configurations. And if your HIL validation fails, you could actually re-choose which configuration you want to do using the reconfiguration mechanism. So
is that guaranteed to be enough? I mean, maybe the variability is very large and you just haven't observed it during workload characterization, and you get this crazy spike during your HIL. Then just tweaking your configuration, I don't think it's going to solve it, right?
Ja, Hogele, de opponent, bedankt voor je vraag. I think that's a typical question in any design flow, I would say, because if it is not a lab or if you do not meet your requirements based on this, then you have to go back. But the hope, or let's say at least this flow, the aim is that will not reach that point.
Okay. Great, thanks. Something a little bit different, but will end up being related in the end. On page 31, you define the function E, which returns for each actor the associated firing delay, right? I assume that's the execution time or the response time?
Hogele, de opponent, bedankt voor je vraag. So in this case, it's indeed execution time.
Okay, so the question I have for every actor have an execution time, and you have this concept of workload. So what is the relationship between the execution times of the actors and the workload for a particular scenario?
Hogele, de opponent, bedankt voor je vraag. So if you see here, so in this particular application, right, the workload is depending on the regions of interest. So the number of regions you have to process. So for example, if for some region you don't have any, let's say, features present, then you don't process that region. So, and if you have more regions to process, then your workload increases in that sense.
Sure, that's the workload, to understand it. How does it relate to the execution time of the actors?
So for the execution time of each actors, it's indeed depends on the platform load as well. So for the platform, you have variabilities due to other interference.
So is the workload, is that somehow the throughput that comes from the execution times of the actors? You know, of course, have execution time of the actors. I can compute a throughput for the graph as a whole. Is that equal to the workload or related to the workload, or what's the relationship?
Could you please clarify?
Okay, so you have a scenario in which you essentially have a data flow graph with execution times on individual actors. From that, you can compute a throughput for that particular scenario. But a scenario is characterized by workload. So my question is, what is the relationship? Is workload the same thing as throughput for that particular scenario, or is it somewhere independently arrived at, or is it an abstraction, or is there no relationship between the two? Maybe I'm missing something. It's quite possible.
Yeah, opponent, bedankt for your vraag. I think it's not independent in that sense. So the workload is, of course, it determines the throughput in that sense. But the workload here is depending on the actual image you receive. So maybe indeed, we have scenarios, that's workload scenarios, and then the scenarios change based on the actual input image. So maybe in the first image, you had 3 regions. In the second image, you only had 1 region that you want to process. So that's how it changes. And that's, of course, if you first say that the workload had 3 regions, then the throughput is different than when you have a workload with 1 region. So that's how that is the throughput and the workload is related.
Okay. Good. Okay, thank you. Then I don't know how much more time I have. Yeah, okay, good. I have some more questions. So if we go to algorithm 2 on page 98, that's kind of the formal description of your figures, such as figure 4.3, right? You have the design flow as a figure and you have it as an algorithm. So my first question is on line 2, you say let map G denote the mapping of the SDFG. On this line, do you now say that map G has been given as an input, or do you compute it at this line?
So in this line, we so this denotes it at this point. But I think you also will have to compute the mapping. So yeah, but then for that there is a different function at line 7, for example. So you map this. So in this in line 2, what you do is you denote map G. Yeah, so map G denotes the mapping of the SDF graph. So it's just denotes that particular one. And then at line 7, for example, you map that particular graph based on the scenario that you are in this case. So at this point, it's just
right. So my question is, what is a mapping? Is this a mapping then of all of the scenarios together, of one particular scenario, or the worst case scenario, or for a set of system scenarios? So what is what are you actually mapping there?
Ja, hooggeloofde opponent, bedankt voor je vraag. So if you go through from line 3 onwards, so it's for each workload scenario you map. So you map. So for each workload scenario, I have an SDF graph, and then I map that SDF graph to the platform. So that's what you see in line 7.
Right. And then you map each individual scenario independently.
Yeah.
Okay. So one of the questions that I had is, at some point in time, you sometimes end up merging scenarios, which is, I think, is a good thing, right? You have fewer scenarios, less switching. So let me try and find the exact question. So when you merge scenarios, what happens then to these mappings of these separate scenarios? Because different scenarios can be mapped very differently, use very different resources. Are you going to take the maximum? Are you going to take the sum? Or what's happening there?
You have to recompute the mapping for the new scenario.
Right. And is there any guarantee that all of this is going to converge somehow? That when you start off with a bunch of scenarios and you start combining them, what happens? I mean, is there any, do you have an idea of the behavior of this system? So if I get to line 41, do I always get there? And ideally, I have the highest quality of control at the lowest cost. But, do I always get to line 41, or can I bail at certain point, or have to jump back?
Hooggeloofde opponent, bedankt voor je vraag. You always reach there. So it's not like... so the convergence comes from the initial choice of the implementation choices, and also based on the frame rate. So in this flow, if you follow it, you will always reach the end.
Okay.
So at least
that's a great answer. Then I'm very satisfied with that. Thank you very much.
Thank you.
Thank you very much, Professor Goossens. Then I would like to invite Professor Voeten to continue with the opposition.
Dank u wel, mevrouw de rector. Geachte promovendus, I would like to congratulate you with fine piece of work in which you develop a methodology to actually develop control laws and the embedded implementation in tandem for these data-intensive systems. My first question actually concerns chapter 2, in which you exploit a scenario where data flow model that capture the workload characteristics. On page 27, you characterize the control problem of a lane keeping assistance system as a linear time invariant system. But then on page 32, you make basically a manual translation to an SADF model. So I actually wondered whether you could actually do this in a more systematic way, or maybe even automated way, to get from the control problem to the basically embedded model, a model of the embedded implementation.
Ja, hooggeloofde opponent, bedankt voor je vraag. First of all, thank you for the compliments. And for this, I think you can indeed do it. So there are, let's say, previous works which talks about how you can do it from, let's say, a control model. For example, in an ISA domain, you can directly transfer it to a data flow graph, but maybe not for the SADF, but to a data flow graph. But here, at least for this case, we do manually because we want to keep it generic. So we don't touch the control and actuate as it is. So any controller design that anyone makes could fit in this flow.
But why do you say it's more generic? So you could capture that, basically the control problem in any which way you like. For instance, the Z domain, and then have that translation. So why, that's also generic. So why is that, did you say?
Ja, de opponent, bedankt voor je vraag. Because in my thesis, the focus mainly is on the sensing part, which is the image-based, let's say, the image processing and how you can optimize the scheduling and throughput for the entire application based on the sensing, because we noticed the sensing is the most compute-intensive part. And for the controller, yeah, I think indeed as a future work, if your controller is also compute-intensive, you could also consider it. But in our case, that was not the case, so we did not fully explore that particular option.
Yeah. Could you extend the method that you just referred to also to SADF? Because that work targeted SDF in a systematic way. Would it be possible to actually generalize that to SADF?
Hello, the opponent, bedankt voor je vraag. I think it would be difficult because in that work, I mean, it's difficult to consider the multi-rate aspect of the system. So I would say it is difficult. So
could you elaborate a bit on that? Why? So the multi-rate seems to be difficult, and
so
is it possible to unroll, for instance, a multi-rate controller to a single-rate controller?
So I think so. If you start looking at unrolling, then you start getting a really complex or big graphs, and then the scalability and the other aspects also come to play. But I think so the previous work that you referred to, from there, I would say it'd be difficult to make it into a multi-rate part and then transfer it to a data flow. Okay. So I think at this point that's what I know, because maybe it's good for a future work how you can do it. So at this point, I don't know how to do it yet.
Okay. So in light of this remark, so this reference to this earlier work, so you make a claim in your thesis. It says this thesis proposes the first formal model-based design framework for the IBC system co-design that relates data flow analysis and control of design. Could you complement? Could you explain that? Also referring to the previous reference again.
Ja, hello, de opponent, bedankt voor je vraag. So I do agree that the previous work relates the data flow analysis and controller design, but it doesn't do co-design. So there are two aspects that's different. That's the application consider, that's the image-based control system, and the co-design aspect. So for the co-design part, in the previous work, you only used the data flow for timing validation. So you transfer the Z-domain model into a data flow model, and then you just check if the timing was met or not. And you do not use the actual timing information to basically optimize your controller. So there was no co-design part involved, but in my work, we do co-design. And then the second aspect is regarding the application itself. So in the previous work of Raymond Frines, if I remember correctly, so there the application had some constraints or assumptions. For example, your delay cannot be more than the sampling period. But in an image-based control system, you could have a delay more than the sampling period. And also in the previous work, you assumed a fixed periodic execution. But in this work, you can have for the image-based control system, you can have a variable period. So I would say, so in my claim, yeah, it's like mostly on the image-based control system co-design, I would say it's still valid. But I agree that the relation was first or made in Raymond's work.
Yeah. That brings me to the next question. So you also discuss pipelined execution, where you basically can improve sampling rate, keep the delay constant. So could you say something about the control performance? What is the most dominant? Is it the sampling rate, or is it actually the latency, the delay in this domain?
Okay. Hello, the opponent, bedankt voor je vraag. So mostly it's the delay indeed, but then there are also some applications where we notice that having a better period also helps. For example, for tracking-based applications, if you give the period too long, then you do not track in between. So there, it also helps to have a better period as well. But if you can reduce the delay, it always increases the performance. But I would say for tracking-based applications, increased period also helps.
Okay, thank you. There's still some time for questions. Then I'll like to go to chapter 3. in which you have this controller synthesis method based on Markovian jump linear systems. First question is, are there any requirements that you pose on the Markov chain that you use to describe this probabilistic behavior? Because in the end, you actually compute steady state. This simply doesn't always exist. So do you have some requirements that you have?
Hooggeloot opponent, bedankt voor je vraag. Indeed, that is a requirement, at least in the current formulation. So you need to have some steady state where there is a recurrent state involved in the Markov system. But I mean, if by analyzing the data you cannot derive such a system, then the current formulation cannot be applied. So that is the current situation. But indeed, in the future, maybe there is you could tune the formulation better, maybe to also accommodate other situations.
Yeah, that brings me to the next. So you refer to a method to actually obtain a realism, a Markov chain. So my question is, how do you do that from learned, observed data? So how do you actually reconstruct or construct a Markov chain? And so also your execution times that already came back, they are fixed. When you actually observe execution time, there are probably many variations. So how do you actually capture that and know what scenario you're actually involved in? So how do you get that Markov chain? Can you elaborate a bit on that?
Ja, hooggeloot opponent, bedankt voor je vraag. So in this case, indeed, I think there is steps involved before. So first is we have a raw data, and then the next what you could do is we do first get a distribution, for example, a PERT distribution. And then once you have that distribution, then we define the initial Markov states based on the classification on the PERT distribution. So you consider the initial region in the PERT distribution as a workload scenario, for example, and then maybe, so you could, and the next part would be the next workload scenario, and then maybe the third workload scenario. And then these three would be the states in your Markov chain, discrete time Markov chain. And then from this, you then compute the probability. So then you know, then you now go back to the raw sequence, for example, and then see what's the transition probabilities between these states. And then you use that data to model the system. At least that's how we approached it. Maybe there is a better way that we have not explored. Probably that's also something has to be looked at in future.
Okay, thank you. I'm satisfied with the answers.
Thank you, Professor Voeten. Then I would like to ask the co-promoter, Dr. Goswami, to continue with the opposition.
Thank you, Mevrouw Rector, Dr. Promovendus. Thank you very much for the nice presentation. I think it was very clear and compact. I do have a few questions that may be interesting to discuss in the remaining time. The first question is related to your uses of the sensing information that you obtain from the images. So, I mean, all the work that you have presented, you have used the image-based information by some algorithm in the feedback part. But there are many applications in reality where the image is used as a feed forward or for let's say modifying the set point. And the question is if those kind of applications are considered, whether the benefit that you have reported will still hold or not.
Via geleerde co-promotor, bedankt voor je vraag. I would say that it would still hold. I mean, I don't see any reason why it shouldn't hold. What will change is already in my my control formulation, I consider feed forward gain, but not as a set point or changing the reference set point. What it would add is like the application model. So what would change is mainly the modeling, but then the approach per se would hold.
The question is, would that still show some benefit?
Yeah, that is something we have to explore, but at least with respect to a timing perspective, I would say, yeah, you can get an improved throughput and latency because if you do a mapping or things like that, you could gain on that. And if you also consider workload variations and approximation, you also gain. But whether that will benefit actually the feed forward or reference point, that's yeah, something I have not looked at in my thesis.
I mean, you have considered constant reference, right? I mean, in your control law, you have a variable which is always constant, and what would happen is that that value will change, and that change in value will be sensed by the image, right? And of course, for the cases that you have considered, the reference is constant, but in that sense, it would need only once the update, whereas for the feedback part, you need the update of the image all the time in all samples. And the question is, if the reference is time varying, would that make more sense there to apply the technique that you have developed?
Sehla, the co-promoter, could you please clarify that, because I...
So in your work, you have considered constant reference, right?
Yeah.
And that's why the static feed forward is also working. Now, if you have a time varying reference, for example, and the reference values are changing over time, and that you can sense by the image. Now, in that case, do you think that the methods that you are proposing would add nearly same benefit or value as it is now doing for the feedback part?
Okay, Sehla, the co-promoter, I think, so you mean like if you use image processing for reference changes, not for measuring the states,
Yeah,
but
exactly.
for changing the reference. Okay, yeah, then I think it would indeed help. So that's what I was talking about before regarding the tracking changes. So if you are tracking reference, then so in my thesis, since I am using a feedback loop on measuring the states, what I do is, so you gain more so I show that the parallelization wins. So you need to first parallelize and then pipeline with the rest of the course. And that's because of the class of system I use. But now if I use image processing to change the reference tracking, then I think the pipelining would win. So because there, of course, the delay is needed, but then at some point you also need to get a better period. So that will also help. So the method per se would work. It would just be the choice. So the design space exploration part would give me a different result than the result I have now.
Absolutely, I am completely satisfied. Let me ask you something slightly different. So, you in your work you have studied two platforms. One is ComSoc, and the other one is NVIDIA a Drive platform. And NVIDIA Drive platform has unpredictable execution behavior, so that's what gave you the challenge, and you have tackled with it. And often you have, let's say, position the platform as something unpredictable. But actually, there is another challenge you faced, and that can be also seen with one of your diagrams in page 48, that you have changed the SDF graph because the platform does not allow you to map as you need, because there is a limited, let's say, scheduling freedom offered by the platform. And you have also tackled that. What do you think about, let's say, bringing that aspect? Let's say, one of the first steps you have in your design flow is binding our graph, right? There you need to map, and you need the mapping freedom, which the platform does not offer. And the way you have tackled it is to change the graph. Now, do you think that should be also part of the automated design flow, or what kind of challenges it brings?
Ja, zeer hallo, de co-promoter. Bedankt voor je vraag. Currently it is indeed like for the industrial adaptation, so I position it as an adaptation rather than part of the automated flow. But indeed, so if in the future we are looking at adopting this for the industrial platforms, indeed, we have to have an automated method to do it. So I think I also put it in part of my future work, how you can get this automated model from the platform or from the application. So I think indeed it should be part, but then that's not something I explored in my work. So in my work, it's mostly manually done.
Yeah, thank you very much. And I'm satisfied.
Thank you very much for the questions. Hora Est has been announced. I kindly thank the opposition for questioning the candidate, and I also thank the candidate for the answers. You may take again your seat in the audience. The committee will now withdraw for deliberation. The meeting is adjourned.